Hi everyone, this is Shiling He from Microsoft Research. In this talk, I will present an empirical study of log analysis at Microsoft. This is a joint work with the Chinese University of Hong Kong, Shenzhen, Azure, and M365. Logs are widely used to record important runtime information about software systems. Engineers can diagnose failures, analyze workflow, make business decisions with the logs. In recent years, automated log analysis is proposed to incorporate intelligence. As shown in the right figure on related publications, this direction becomes more and more popular. However, the real voices from frontline practitioners in industry are seldom heard. For example, what kinds of logs do they analyze? What tools do they currently use and want to use? Do they have any troubles when analyzing the logs? From what we observed, there is a gap between the industry and the research. That's why we started this work. We conducted an empirical survey study on log analysis at Microsoft, one of the largest software companies in the world. The survey covers very diverse products, including the cloud system Azure, search engine Bing, social media LinkedIn, productivity applications like M365 Office, and operating system like Windows. Besides, we made some discussions on common practice, gaps, and opportunities regarding for representative log analysis scenarios, including logging, log parsing, anomaly detection, and failure diagnosis. To start the survey, we iteratively revised the survey questions for several rounds and finally produced a questionnaire of 13 questions. As listed in the right figure, the first 11 questions cover four important perspectives ranging from participants' role, log usage, log analysis, tool support, and challenges. The last two questions are about the follow-up interview and suggestions. We took a hybrid method to recruit the survey participants and distribute the questionnaire, such as posting invitations at internal communities and snowball sampling. At last, we collected 105 survey responses and invited 12 participants to attend a follow-up interview for about an hour. As shown in the below tables, most of them are engineers and developers with at least 5 years of working experience. The first log use question is, which log format do you analyze most frequently? Typically, there are three types of logs, including structured, unstructured, and semi-structured, as shown in the left table. We find that the most common one in industry is the structured logs with a portion of 41%, while in research community, the major type for study is the unstructured logs. The second question is, which scenarios do you usually use logs for? There are multiple options for selection. Not surprisingly, the most voted scenario is root cause analysis, in which logs are used to troubleshoot the reasons for failure or performance issue. We are also curious about the time spent on analyzing logs. It can be observed that over half of participants spent more than an hour on log analysis for each incident. Note that most participants are very experienced engineers. Therefore, it is still a heavy workload to analyze logs, and more automated tools are needed. For log analysis tool support, the results are as follows. First, for log analysis methods, most engineers use keyword search to find related logs, or statistical analysis such as count, sum, and trend analysis to understand the logs. There is still a small portion of engineers read logs line by line to understand log content. To conclude, current in-use log analysis methods are relatively simple, leaving space for more advanced tools. Regarding the specific tools, there are generally four types, including database query, data analysis tools such as Python script, editors like VS Code, and dedicated tools like Windows Event Viewer. We find most engineers analyze logs directly in the database for its ease of use. We also asked engineers' expectation on future tools that they want in log analysis. Most participants expected intelligent tools, for example, a super AI that provides automated insights based on the given logs. In addition, they also want a good visualization tool to better understand logs and the behind workflow. In terms of the challenges for analyzing logs, we had two findings. First, a large portion of participants frequently work on unfamiliar logs, while only few participants never work on unfamiliar logs. Therefore, it is worth exploring how to ease engineers' burden of understanding unfamiliar logs. The second finding is most participants agree that it is hard to distinguish failure-related logs from normal ones. The last question is to ask participants to provide the pain points and challenges of log analysis in free text, and we group these results into 6 categories by open coding. The first challenge is too many logs and missing logs. For example, many engineers reported that there are too many logs for an incident. Meanwhile, some participants complain that the information from the logs is very limited. The second pain point is that logs are hard to structurize. Therefore, engineers cannot summarize or count for these logs. The third category is logs are difficult to understand. Besides, engineers often feel that finding failure-related logs is often non-trivial. For example, we don't know whether the information is expected or not. The last major pain point is about cross-source correlation of logs. This requires interpretation, which is, however, not always self-evident and usually requires digging. For more details, please feel free to read our papers. Next, I will present the current practice, gaps, and opportunities for 4 log analysis scenarios. Logging refers to the process of inserting logging statements into the source code during the development phase. Currently, engineers usually write the loggings based on their experience. We find that there is a lack of off-the-shelf logging tools. Besides, the logging should consider the log usage. That is, the generated logging statements should be readable and consistent. Log parsing aims to transform the unstructured logs into structured ones with events. In practice, most people use the regular expression to parse the logs. However, we also observed some product teams using a different method, which we name it as event pre-assignment. The basic idea is during the development, after engineers commit the code and merge the pull requests, a logging action will be automatically triggered. The action will provide the source code and insert a randomly generated and unique event ID string to each newly added logging statement. In this way, the event ID will be printed together with the log message during the execution. So the gap is that researchers are leveraging data-driven techniques in log parsing, which however can be easily achieved by lightweight instrumentations. But the above technique cannot work in scenarios where we cannot access the source code, for example, third-party libraries. Therefore, one potential opportunity is to explore the possibility for some dynamic instrumentations to attach an event ID. Regarding the anomaly detection in industry, it usually refers to the process of detecting failures for a software component. We use the term failure alerting to denote it. Failure alerting consumes the metric data and raises an alert when there is an anomaly on the time series data. In research, it is a different story, as it aims to find out whether a log sequence is abnormal. The following table shows differences between the log-based anomaly detection research and the failure alerting in industry from multiple perspectives, including the goal, processing, technique, efficiency, interpretability, and noises. For example, failure alerting usually leverages time series anomaly detection techniques like K-sigma, and they are real-time. But the log-based anomaly detection uses various advanced techniques trying to find out abnormal log sequences, and most of them are not real-time processing. To address these gaps, many opportunities could rise. For example, interpretable anomaly detection. Also, we need to identify which subset of logs are more likely to reflect the root cause of a failure. Failure diagnosis aims to find out hints towards the root cause. We find that research and industry are well aligned when diagnosing batch failures, which happens in a batch and shares the same root cause. The basic idea is to contrast logs from the bad cases and with logs from the good cases. And differentiating logs are often related to the root cause. However, if there is only one failure case, it will be very difficult, such as the custom reporting issues. Therefore, more efforts should be devoted to those individual failures. Another potential opportunity is to automate the human knowledge, for example, automatically executing the troubleshooting guide. To summarize, in this work, we share the voices from real-world log analysis users, including their current status, pain points, and expectations. We also show the current practice, gap, and opportunities regarding for log analysis scenarios. We hope the unnoticed yet significant gap between industry and academia could inspire interesting future directions that converge both sides' efforts and benefit the log analysis community. Thanks.